Hello and welcome everybody. This talk is going to be about improving code recommendations by combining neural and classical machine learning architectures. Please let me first introduce ourselves, the research team behind this. My name is Max Schumacher and I'm currently studying in Potsdam in my master's. My two colleagues, Kim-Tu-Yin Lee and Professor Dr. Arthur Andeszak, are both working at the Group for Parallel and Distributed Systems in the University of Heidelberg. This is also where this work was created. So let's first talk about why we are actually interested in finding good code recommendations. Code recommendations have the main goal of accelerating software development. Most of you probably know it from an IDE, integrated development environment, such as Visual Studio Code. On the right-hand side, you can see such a code recommendation where we have the object self and use some function, which is called assert code execution. And by the third time we do it, the IDE already knows that we want to execute this function and recommends it, which is quite obvious. So this is then used to help developers to either navigate code, prevent semantic and syntactic errors, find function arguments, or simply to automatically generate code. The problem with this is then that dynamic languages like Python miss type information at editing time. And most of the very successful code recommendation algorithms utilize those type information. So the main goal of this talk is to find out how to improve code recommendations. And firstly, we want you to understand how to generate code and which difficulties might arise when doing it. And for this, we'll explore existing approaches to code completion. Secondly, we will talk about ensemble methods for code. So we will combine models and show the potential of such ensemble methods. And lastly, we'll follow up with a comparison of these methods to fuel the discussion on how we can tackle the problem of code recommendation for dynamic languages as Python, and then to finally understand how to do this. So to learn code recommendations, we need some form of representation. And the approaches we're going to look at today mostly use abstract syntax trees. Abstract syntax trees are an alternative representation to regular code. On the left-hand side, you can see some code snippet. It's one we had before, where we have some function, and then in that function, we execute another function. And we can display this by passing it into a tree structure, and this is just an alternative representation. And we can then go on and either flatten this tree into a sequence, or we can work on a tree directly. So for some architectures, we need a flat representation of the tree, for example, in an array. So we can transform this entity into a sequence by a depth first, left to right traversal, where we first go down in the tree and then go from left to right and visit those nodes in this order. And this way we get, for one tree, we always get the same representation, and we have a well-defined representation of our flattened AST. And now we essentially have a sequential learning problem, and this is actually a sequential learning problem in natural language because we treat code as natural language. And what we then can do is utilize neural architectures such as recurrent neural networks. So the first architecture we're looking at actually uses a neural architecture within. It was first presented by Lee et al. In Code Completion with Neural Attention and Pointer Networks. And it has two components: an attentional LSTM, long short-term memory, recurrent neural network, and also a pointer network. Starting point for this approach is a flattened AST, and we take this flattened AST and pass it through LSTM RNN architecture, and then we arrive at this output, which is denoted as switch, and then the switch can decide between two possible outcomes. One, we can predict from some global vocabulary in which we have predefined some words, which could be possible recommendations. Or alternatively, because this might be finite, we can point back to our input sequence and predict a word from the input sequence. And this is actually great if words reappear really often in the input sequence. But we will have one problem here, and the problem arises if the word is not in the vocabulary nor in the input window. And if this case arises, then the network cannot give a correct prediction because neither the pointer network nor the normal output of the LSTM can predict this word. So now let's look at the second approach, which actually operates on the AST directly. And this is called Probabilistic Higher Order Grammar, short PHOG, and it was first introduced by Rajev et al. And here we have some grammar rules, A follows B, but unlike in a classical grammar, we don't just take the grammar rule, A follows B, but we take an additional context. And we generate this context by iterating over the AST. And while we visit the nodes of the AST, we keep track of any interesting values, types, or positions to find out what context the actual prediction is in. So let's look at an example for this. So we are currently at this leaf node name load, and we want to know what value it is. So we have a prediction problem. And in this case, the context is simply the last leaf node where we had some naming parameter, and this is self. Actually, this is already what we wanted to predict. But now we visited the nodes of the AST and we generated this context. And now we can use this grammar rule, A follows B, and form a higher order grammar rule. So we have this leaf node name load. We take our context and parameterize the rule with it, and then formulate a higher order rule, which then gives self our final prediction. Okay, so now that we have this, how can we utilize it for the pointer mixture network? Okay, so now how do we do this? So we combine pointer mixture network and PHOG in something we call an extended network. And this so-called extended network has three components. It consists of both pointer mixture network and PHOG, and a third component, which is similar as we've seen before in the pointer mixture network, a switching mechanism. And now how do we make a prediction? So we introduce something called a special ID. And the special ID is just a keyword which tells us to use some other model. In this case, if the special ID occurs, use PHOG. So how this prediction works is we receive the AST at the neural network, we form a prediction, and then we'll simply check, is the prediction our special ID? If so, then we'll utilize the prediction from the PHOG, and if not, then we will use the pointer mixture network. So now let's take a look at some sample predictions from the extended network. This is a code snippet from our training data, and it has just a bunch of test functions. And here we make the first prediction with the argument self. So this is a true prediction, and it's predicted by the RNN, and this word self appears often, so it is in our vocabulary. Okay, so then we will predict self again. This again is easy. It's not really that hard to predict this keyword because it's appearing this often. So then we'll move to the first problem where we have a false prediction, and for this value, assert code execution, we cannot predict the keyword just yet because it's not in our vocabulary, and also the other components can't or don't formulate a correct prediction. Okay, so then we move on. We have the keyword self again, self again. Okay, so now we have another case. We arrive at this prediction or assert code execution again, but now it's appearing a second time. So here we can see how the pointer network kicks in. So the pointer network can now, because this already appeared in the code, point back to this position and therefore formulate this prediction. And this is a true prediction by the pointer network. Okay, next, we've seen that self is predictable and it's not hard to predict, but in this case we fail. Also, we have again assert code execution, and now it should be predictable by the pointer network, but we fail. Okay, and lastly, we'll have again assert code execution. This time it's predicted by the PHOG. So now arises the question, how do we deal with this case? Should this be predicted by the pointer network or by by the p-hawk, and how can we choose the model? So how do we actually choose a model? So for this, we define a set of conditions that determine our targets, C from C0 to ZK. And then for some AST, where we want to make a prediction, pred, we iterate over the condition C. And our target is then just the smallest index where our condition holds to true. So let's look at an example. The behavior we want is to utilize the p-hawk whenever the pointer mixture network fails. So first, we'll see if the prediction is in the vocabulary. If so, then the target will be 0, because Z0 is true. If not, we'll move to the next condition. C1. If the prediction is in the input window, then, if this is true, we'll use the pointer component. Now, if C0 and Z1 are false, we can check if the p-hawk produces a good prediction, so if it's correct. And if so, we'll use the special ID as a target, and therefore we've defined how the extended network should choose the right model in a given scenario. So that's the wanted behavior. Now we'll just quickly talk about a more general definition of an extended network, so for arbitrary many models. So we have some neural network with the regular output nodes, and we can add as many models as we like. So in this case, it's case statistical language models, and each of these models becomes an extra node in the output layer of our neural network. So the output will just be your regular output of a neural network with activation function and bias and so on. And then what we need else is a set of conditions which define the wanted behavior, so how the model is going to work as an ensemble. So now let's come to the experiment section and the evaluation. So we use the very famous 150K Python dataset, which was created by ETH Zurich. And this was also used in previous works, which is nice for comparison. So we have 100,000 AST for training and tuning and 50,000 for evaluation. So we'll first evaluate a vanilla extended network. Then we'll evaluate different RNN architectures. Then we'll look at a special case, which are empty values. And we'll conclude with a model comparison. So first, we compare the individual components to the ensemble prediction. So we have p-hawk with accuracy on the test dataset with 63.8%, pointer mixture network with 66.4%, and then our model, which is the extended network, with 67.0%. And we use the same hyperparameters for evaluating the pointer mixture network and an extended network. And this way, we ensure an isolation of the effect of implementing an ensemble rather than improving the underlying models. So we can see that an ensemble improves over the standalone models, which is important. So after seeing that the concept works, we can then move on and try to improve the underlying models. And in this case, we took single and two-layer LSTMs and used some appropriate form of dropout. And then we evaluated this on a train and test dataset, and we got the best model using a two-layer network with 20% of dropout. So this brings us to the final model of the extended network. And here we used a vocabulary size of 10,000 words. Then, as seen before, we used the best configuration, so a two-layer LSTM with 20% dropout, but otherwise kept the same hyperparameters as the pointer mixture network. And by doing this, we could see a final accuracy of 69.3%. So while conducting our evaluation, we found out some interesting distribution of the values, namely that almost 50% of AST nodes do not have a value, and this is encoded as empty. And both p-hawk and pointer mixture network includes these by the keyword empty as a possible value. So the problem we have here is then that the empty value is eventually too easy or easier to predict, in which case we would overestimate the accuracies. And a solution to this would be to evaluate more conservatively, where we could exclude the empty values in the evaluation. So when actually excluding the empty values, we can observe some very interesting behavior. So we compare the components with empty values and the components without empty values. So two scenarios. We can see different behavior between the components. So the RNN drastically drops in performance, so from 54.1% accuracy to 18.8% accuracy, while pointer component and phawk drastically improve, which is a very interesting behavior and shows the importance of digging deeper into this problem. So on the one hand, today we've seen extended network as an ensemble method, and we've proven by implementing one that the concept works. Also, we've seen that we can build arbitrary large ensembles with this method. But also, on the other hand, we want to point out that the state of the field is moving very fast, and we want to hint another method, which is the transformer models. And it's presented in 2020 by Sin et al. In the paper Code Prediction by Feeding Trees to Transformers. And we advise you to take a look at it. Thank you and goodbye.